All right, welcome to class. Happy Friday. Getting your weekend off with a bang here. Finishing up chapter 3, right? So, homework for chapter 3, homework assignment number 3 will be due tonight. Make sure you get that uploaded Learning Suite. Don't wait until midnight to do it. We had a couple people had trouble submitting homework 2. We can help you out with that, but don't don't do that. It requires quite a bit more work then. But let's see. So, chapter 4 on Monday, alkanes, and that will be the last topic before test 1. So, we have these 4 preliminary chapters, you could say. Chapters 1 and 2 are really kind of review materials, and 3 to some extent. If you remember your forces, your basic forces and structure linked together, chapter 3 is not too bad that way, but Chapter 4, now alkenes, is entirely dedicated to organic compounds, and that's a class of compounds. We've already talked about what alkanes are. All sigma bonds with carbon-carbon, carbon-hydrogen bonding. We'll look at isomers and some reactivity. There are some reactions in the alkane chapter. You'll see what those are. But naming will be a part of that too. So we'll do the systematic IUPAC naming coming up for that. But, and then test 1 here, yes, it is in the testing center. There were some concerns about the testing center on the questionnaire. I'll call over there again and touch base with them, but we have gotten details on their protocols they're doing over there. There's distancing, they sanitize everything really well. The line conditions is the big concern for me, for you guys getting in and out of there in a timely manner. So I'll check on that. We haven't really had a lot of tests over there yet. I haven't talked to any. You know if anybody's had a test in the testing center yet? Anybody? No, yeah. So it's just coming up here, but we should be okay. If there are major issues or whatever, we'll come up with another way to have you take the test. Okay, so we'll help you out there, monitor the situation. But yeah, we'll be in the testing center. That's Monday and Tuesday. Tuesday will be the late day, so I think after 3 in the afternoon you will be charged. I don't get any of that money. That's a requirement now of the testing center. For years we fought as a department against that. We did not like that idea, but that helps students, I think, take the tests a little earlier, so it will be available that Monday, whatever. Okay, so last time we did do these intermolecular forces, the forces that hold molecules together. So we've done bonding, right? And now we're talking about something a little more dynamic, kind of like acid-base theory, you could say. You know, we've got, instead of donating a proton from an acid to a base, here we're talking about what is it about the structure that engenders something about the properties, okay? So it has to do with polarity and bonding. Polarity to the extreme, maybe. We will look at ionic bonding in the case of some compounds. But it gets very detailed now, especially, I think, with the nonpolar interactions, because we have some very subtle effects with branching. And I already introduced that with the octane molecules we'll get to in a second. But just to review the properties real quick, van der Waals, that's kind of a funny name. Those are dispersion forces or temporary or induced dipole-dipole interactions. That's what nonpolar molecules typically undergo. So the carbon framework there with the carbon-hydrogen nonpolar bonds, those are your typical forces there. They're very weak, but a big molecule, you know, those forces can build up and it can be significant for the properties of the molecule. Then we got permanent dipole-dipole interactions. So you have to have a heteroatom or a Z atom there. Usually it's a carbon-oxygen, carbon-nitrogen, or carbon-halogen bond, something that's more electronegative than carbon. And that's a permanent unequal distribution of those electrons. So there is a partial positive, partial negative end, and that can affect the properties significantly. And then stronger still, hydrogen bonding, which is really just a subset, I think, of dipole-dipole, where you have a hydrogen, a small polarizable atom, right? Low electronegativity, it's 2.2 on the Pauling scale, bonded to an oxygen or a nitrogen, then you can get hydrogen bonding with itself, okay, within the pure molecule, or that will affect significantly what? Water solubility. That's another property we're covering today. Notice it also includes HF. if there's a hydrogen on a fluoride. But that means the fluoride can't be bonded to anything else. So we're really not talking about alkyl fluorides or alkyl halides, although those are polar bonds. You need the hydrogen on the fluoride, which really limits it to just that one simple molecule, HF. That's not an organic compound, right? So the ones you got to worry about are the hydrogens in alcohols and amines, or carboxylic acids, right? Anything with an OH group there. So we kind of link this to the functional groups, right? Those 16 you need to keep track of. And then the strongest force up here is what? Ionic, electrostatic forces with salts. And the typical ones shown there are inorganic, right? Sodium chloride, lithium fluoride. Who cares about that? This is the no-chem class. Well, some organic molecules can have salt components, right? They can be ionic, along with a nonpolar part. So they can be these amphiphilic type molecules with dual character. And we'll see those with soap and detergents and a couple other applications here in a second. So let's go to the board if there's any questions on these forces. And we gave you the magnitude of these forces. We gave you some kcal numbers. Don't memorize those, but be aware of the magnitude differences here, okay? So here's some molecules. What did we leave off with the last time? Octane and gasoline, okay? Both straight chain or N-octane. Don't worry about the naming yet of that, but we'll get to that in chapter 4 coming up. And this is isooctane, highly branched material. They're both the same molecular formula. What are they? C8H, count up all the hydrogens here. What is it? 18? Should be able to come up with the 18 there. But they're very different in their boiling points. This one's what, 125 degrees C? And this one's what? What did we say? 99 degrees Celsius. So which one can vaporize more easily as you heat these up? Well, this one is more volatile, okay? And what is it? This is carbon-hydrogen bonds. So we're talking about what? Van der Waals interactions, induced dipole-dipole. Notice the surface area of this linear one is going to be quite large. It's a long cigar-shaped bag of electrons sloshing around, okay? And when they bump into each other at any time there, you can have a partially negative and partially positive end of this molecule. That's an induced dipole. That's not a permanent one. But because of the larger surface area, what? Those van der Waals forces are stronger than something that's what? More spherical shaped. Okay? It's more ball shaped. That has a lower surface area. Yeah, you can induce a dipole here, but notice the dipoles would be closer together and they'd be weaker in magnitude. And this one would be more easily able to escape the liquid phase. It is a liquid at room temperature. Room temperature in Celsius, that's another thing you should keep in mind to kind of gauge yourself. What's room temperature in Celsius? Fahrenheit, it's what, 73, 75, depending on your thermostat. What is room temperature in Celsius? Yeah. 20, 23 degrees, yeah. Unless you're in Phoenix and then it's 40 degrees or so. Yeah, so I don't know. It's always kind of relative. But keep that in mind, about 20, 25 degrees. That's well below this. So this would be a liquid at room temperature, right? Okay. Anything that would have a boiling point below 20 would be a gas at room temperature. So yeah, gauge yourself there. You know, physically interact at least that way with this molecule. You guys interact with these molecules all the time when you fill up at the pump, right? And I mentioned the octane rating, and that's an engineering thing, how well an engine works with these two fuels present. This one has an octane rating of 0. That will knock your engine apart. And that's because it won't completely combust during the expansion phase of the piston. And during the compression phase, some will still be left because of the speed of the combustion wasn't as fast. And you'll get the rod knocking, okay? This one's just a little more volatile, right? 26 degrees, a lower boiling point. This one has an octane rating of 100. And most commercial gasolines are a blend. A lot of straight chains will come out of petroleum. We'll talk about that in chapter 4. Don't worry about that. But you'll blend in more of these branched hydrocarbons. And again, branching is the key idea here. We'll see it in a number of places. What? This isn't just 8 carbons in a row. This has, you know, a couple of methyls here sprinkled in. and makes it more spherical shaped here. The naming in chapter 4 will help out here to see the branching. But if you have branching here, the boiling point tends to what? Go down, okay, because of the smaller surface area. Okay, so that's a function of the structure having to do with the properties, with these very weak forces. But you see this difference in boiling point, and then the performance in the engine is significant that way. Yeah.
So for the octane rating, 100 is like the perfect.
You can go over. You can have octane ratings of 120. Aviation fuels. We'll talk about that. Nitromethane. You heard of nitrous fuels, maybe? Any motorheads out there? Maybe some. Okay, yeah. So someone's asking, about the octane rating. Don't worry about that. The physical properties here, the branching and the boiling point, comparing them. Don't memorize these numbers, but know if there's more branching, you expect it to be more volatile. By volatile, I mean it's easier to escape the surface area of the liquid. By the way, what is really the basis for boiling a material? We're talking about organic molecules that have weak intermolecular forces compared to ionic compounds, right? So when we talk about boiling point, what is really the boiling point? That's where the inherent vapor pressure of the material equals what? The applied pressure of the container it's in, okay? So by raising the temperature, you increase the vapor pressure of the material that's balanced with the applied atmospheric pressure. We could get into a lot of details of that. These numbers are at standard conditions, 1 atmosphere conditions. 760 torr. So maybe you remember STP conditions from Gen Chem. So here we're kind of doing them all at the same position, but it's the applied vapor pressure. The applied pressure of the container to the inherent vapor pressure of the material. Okay. Anyway, don't worry about that. That's how well it escapes. This is an interesting one. Cubane. And cubane's a little bit different here. Let's see, I hesitate to put that up there sometimes because cubane is what? C8H8. And we've got these methine carbons at the corners of a regular cube here. Highly strained compound here, but you can make these type of materials, okay? And notice it's what? Lighter, only having 8 hydrogens. What about its boiling point? Who read the chapter and can tell us something about it? Is this boiling point going to be higher than these or lower? Lower molecular weight. You might say, well, is there more branching here? Maybe, which would argue for this being even lower, right? But what is the boiling point? Anybody? It's 161. Wow. Why is it so high? Let's see. This is a very, yes, please. Very good. So someone points out that it packs well in the solid, so it has good lattice energy in the solid state, and that's because of the high symmetry of the molecule. It is a little ball-shaped molecule, and spheres can pack together very well in the solid state. So it's symmetrical, highly symmetrical. This will tend to have what? Higher intermolecular forces because of the packing, especially seen in very symmetric molecules. I'll show you a couple others where that might be an issue. Yeah, but 161 for the boiling point there is very, very wild. All right, let's look at these molecules here across the bottom. Here we got these 4. Let's compare the boiling points there. And here we're kind of showing you the functional groups and introducing more of the properties here. So an alkane, pentane here, 36 degrees. It's almost a gas. Okay, butane, maybe you've heard of butane lighters and propane. We'll look at those. Those are gases at room temperature. They need to be contained. Here's the first one that's a liquid, actually, in the hydrocarbon series, 36. Again, I'll memorize the number, but the comparison to the other functional groups of comparable molecular weights is important here. The aldehyde, 76. Why is it so much higher? The aldehyde. What's the force now? Hydrogen bonding. This hydrogen's on a carbon, so I wouldn't say hydrogen bonding. What's the other property you'd want to? Not resonance? Okay. What's the other? Look at the table if you need to. Dipole, dipole. So you got partial plus, partial negative here, and those can line up with each other. And because of their permanent dipoles, this is just induced dipole. So it requires less energy to vaporize it. Here you need more energy to vaporize because of the dipole-dipole interactions, okay? So you see the trend there. Oh, what about this one? You mentioned this one. There's the one you want to mention, hydrogen bonding. So what do you predict? Higher boiling point or lower boiling point? Higher, yeah, and quite a bit so, 118, okay? Higher boiling than water. It's got this one that can certainly hydrogen bond with itself. And that'll affect water solubility too. We'll get to that, but these type of interactions can be significant, and that increases the forces between them. And then carboxylic acid has the dipole-dipole thing going on and hydrogen bonding. In fact, these guys are symmetrical enough, the functional groups, they can kind of sit like this and form these dimeric hydrogen bonds, the geometry of that. So what would you predict here? Higher still, right? 186. Wow. Okay. So carboxylic acids tend to be the highest boiling there. But, you know, molecular weight can play a factor too. All right, let's look at the hydrocarbons here of pentane, a little more detail, 36 degrees. Let's look at this one. So here we got branching going on, and we got more branching. Let's look at the boiling point. So we start at 36 degrees here. What do you predict for this one? A little bit more branching, right? A little bit more spherical. So what would you say, lower or higher melting boiling point? A little bit lower, 20, 28, not much. Okay. And what about this one? Yeah, lower still, 10 degrees. Okay, so that's a gas at room temperature. This one's real close. In Phoenix, that would be a gas. Maybe here in this room, it would be a liquid, but not very much. Wouldn't require too much more energy to get that to go. Okay, those are boiling points. Let's see, I've got melting points here also. So melting, we're talking about going transition from solid to liquid, okay? It's already mentioned there. So here you have to be a little bit careful about symmetry. In general, branching will lower melting points also. It's a little bit easier to escape if it's a smaller surface area. But when it becomes highly symmetric, all of a sudden the melting point can jump way up, like we saw with cubane, the octane that was all in a cube like that. So let's see the melting points here. I think I've got them minus 130 degrees. See? So that's pretty low, right? Those are weak intermolecular forces. Compare that to ionic salt, right? Sodium chloride, where the melting point is what, like 1200 degrees? Okay. So very different properties here with this molecule. Minus 130. And then right here, this one, minus 160. And that kind of fits. It's a lower melting point because of the branching. But watch out here. Neopentane, minus 17 degrees. And that's because of the symmetry. This one is spherical, it's ball shaped, so in the solid state, it can pack more efficiently and take better use of the volume in the solid state. So if you see something that's highly symmetric, think about the melting point especially going way up, okay? We didn't really see that with the boiling point in this case. We saw it with cubane. So that's kind of a fickle property. Don't worry about that. But no, be aware of that, that if something's highly symmetric, ball-shaped, completely spherical, and that's the most efficient use of surface area, right? A sphere. Anything that's elongated or chunky or discontinuous is not efficiently using the three-dimensional surface area. But if it's a ball, that's the most efficient for that. All right, water solubility. Let's talk about this. So what have we got? We've got the ability to interact with water. So yeah, that's usually what we're talking about with solubility. We can talk about solubility in nonpolar solvents as well. But with water, you know, it's the universal solvent for biology, living tissues, or in aqueous solutions. A lot of times we do reactions in water. It's cheap. It's polar. It can solve it a lot of things that are polar enough. But a lot of organic molecules we want to react are nonpolar. So we'll use what? Nonpolar organic solvents. So the solvent has to be chosen to match the properties of what's going on. But to talk about it, to get started, I think is okay there. So what we're talking about solubility, we need about 3 grams or greater than 3 grams per 100 milliliters of water to be considered soluble. Anything lower than that, we call it non-soluble. And right around 3 grams or 5 grams is kind of a transition point, you know. And if it's not soluble, if it's a liquid, it'll form a separate phase, right? It will oil out, and you'll see the 2 different phases. So you can shake things together that are not miscible, and you'll get a temporary emulsion, it's called, but eventually it will separate out. Okay, we need to think about why that is. But let's look at the functional groups and see here. Something like carbon tetrachloride. You might think, well, you got 4 very polar carbon chlorine bonds, right? Dipole moments all over the place. But the overall molecular dipole moment, what? Balances out. So this is actually 0 Debye's polarity. And you can't hydrogen bond to these lone pairs on chlorine. You might think, well, there's 3 lone pairs on each halogen, right? And that is a partially negative end. But those lone pairs, because of the electronegativities, are held very close to the chloride, and they're not able to participate in hydrogen bonding with water. So this is insoluble. Well, it's a tiny amount that will go into water. But if you mix carbon tet and water, you can shake them, form a temporary emulsion, but they'll separate out. It turns out carbon tet is more dense than water, so the carbon tetrachloride layer will actually be on the bottom, and there'll be a barrier between the 2 solutions. So it's kind of a mysterious thing here. But how about this? Acetone. Now that molecule, has 2 nonpolar methyl groups here, but it has a polar, right? Significantly polar dipole moment here. So that partial negative end, partial positive end, can actually interact with the water in this way and be what? A hydrogen bond acceptor, okay? Now the water, the negative end, kind of has a hard time getting close to this carbon here. Why? It's got to get in here close to these 2 nonpolar methyl groups. So this isn't a big factor. But this hydrogen bond acceptance from a water molecule is significant. And there's another lone pair over here that can do the same thing. So what do we say about acetone? Is it soluble or not? Yes, it is soluble. Okay. Yeah, and it's small enough to be miscible at all concentrations there. How about ethanol? Now we have 2 nonpolar carbons, right? But what? A lot of hydrogen bonding capabilities here, there, and here. Just make sure you get them with the right ones, the oxygen lone pair, and then this hydrogen. This one can be a hydrogen bond donor, hydroxyl, right? So this one is definitely infinitely soluble at all concentrations. We'll see some variations there, depending on what the alcohol is, though. Let's see. How about this one? Here we have a longer chain, right? Soluble or not soluble in water? What would you say? There's actually a rule invoked in chapter 3. What is it? If you have a polar functional group, you can have up to 5 nonpolar carbons, and it will still be considered soluble. It'll be in this range of more than 3 grams per 100 mils. So here we only have 4. So what is this? It's 7.3 grams per 100 mils. Which means butyl alcohol, if you exceed this amount of butyl alcohol in 100 grams, it will begin to form a separate layer, okay? So it's not infinitely soluble like ethanol, but it's certainly soluble, we'd say, because this number is higher than 3. Okay, what about this one? I did this one as a demo. It was right at the end. We were kind of rushing that day, but we did N-octanol and water. And it turns out N-octanol is what? Soluble in water? Not soluble. And why? I think you can see why. Here we have hydrogen bonding, but here we have 8 nonpolar carbons, right? And so we have an issue there. We can't solvate these easily. Yeah, well, let's see how soluble is it. Oh, zero point 0.3 grams. I have the numbers here for it in a liter of water. So that's a trace amount going into a liter. That's way below 3 grams per 100 mils, right? So we say this one is not soluble. Yes, that's measured. That's an empirical measurement that can be done. Yeah. So someone was asking about how do these numbers come about? Yeah, there are values for these. You can look them up. Your book doesn't really give you a bunch of these numbers, and I kind of hesitate to do that. Uh, I want you to compare different compounds. So of these three alcohols, which one is the most water soluble and why? It'd be this one. Okay. Which one's the least? This one. Okay. We need to talk about one other thing here: hydrophobic effect. Hydrophobic. And what does hydrophobic mean? Phobia means to hate or to fear. And what does this molecule hate or fear? Water, right? And why is that? Well, it's got more nonpolar carbons than the other alcohols. What's the basis of this hydrophobic effect? You know, the dogma is, well, like dissolves like. Oils prefer nonpolar things and water prefers polar things. Well, why? What are we talking about with the hydrophobic effect? Well, let's go back to the Gibbs free energy expression. And that's always a function of the bonds minus T times the change in entropy. So enthalpy is the bonding thing here, right? Hydrogen bonds or whatever bonds we've been talking about. And then what is delta S? That's entropy. And that has to do with what? The randomness or the disorder of the system. Nature favors disorder. Chaos is a good thing when it comes to free energy. There's more freedom. There's more states that molecules can adopt. They want to do that. They want to escape and do their own thing. That's what entropy has to do. And so if you have entropy increasing here, if it's positive, depending on the Kelvin temperature here, this is absolute temperature. If this is what, increasing or positive, the minus here means what? That this is contributing. The more negative the free energy is, the more favorable the interaction is, right? So this is the bonding overall. If going to more stable bonds, that's also a negative thing. And minus T, if S is increasing, that will make things better, okay? But look at this. Okay, so water can hydrogen bond with this part. Yeah, okay. And, you know, uh, that's contributing to this. In fact, that's significant. You're still getting a lot of good enthalpy here by putting this in water. In fact, you're getting some good enthalpy interactions here because you can induce a dipole here, a temporary dipole, right? And you can line that up with the dipoles of the water. So why is N-butyl alcohol not soluble in water? Well, it has to do with this. As you have this non-polar part here, you're forcing the solvent water molecules to become more ordered around this non-polar part. And delta S here is becoming what? Not more random, it's becoming more negative. Okay, and that's the basis of the hydrophobic effect right there, the change in randomness. Okay, minus a minus, that makes this more plus, which makes it less favorable. And these numbers can be calculated. There's a lot of people who do research on the hydrophobic effect. We'll see it later on when we talk about protein folding, when we talk about peptides and how they fold up the enzymes and the different biological molecules. A lot of this has to do with this hydrophobic effect, okay? But don't sweat this. You know, I'm not going to make you derive anything mathematically here. But the hydrophobic effect is mainly an idea of order, okay? You're increasing the ordering around this nonpolar part of the molecule. And that overcomes the favorable entropy actually here for the system, okay? Yeah, which, you know, there's two terms here in free energy, right? Bonding favorability and also disorder, randomness. That favors more free energy load. Anyway, yeah, I think you're okay there. That's enough to say on that. Yeah, halides tend to be not soluble in water. Let me give you one here that's a little smaller. So here's the one compared to ethanol, right? Ethyl chloride. You know, I think, well, that's a strong dipole moment there. That should be soluble in water. Let me give you the number. I think I've got it for that. Where is it? Where'd I put it? Oh, there it is. 0.45 grams per 100 mils. So that's way below the 3 grams per 100 mole, okay? And that's because you don't get the hydrogen bonding here. These lone pairs are held too tight. You don't hydrogen bond with water, okay? And then you got the greasy ethyl group that you have in ethanol, but ethanol is infinitely soluble there. All right, let's see. Yeah, let's go through these last topics on the overhead up here again, and switching back over there. Again, don't memorize any of these numbers. Be able to compare. I've got another series we'll compare in a minute here in class, but there's the forces again. Here's the branching idea that we see with pentane versus neopentane, which is highly spherical in its shape. So which one's going to be more volatile? Well, the one with the weaker induced dipole-dipole interaction, that's the more ball-shaped one. Okay, this one's elongated. You have a longer distance here and a larger surface area. So that one in the condensed state has what? Higher cohesion between the molecules and can lead to what? A higher melting, boiling point and melting point here. Okay. Here's the basis of what we're talking about, distillation. You've probably had some lab classes or done this. You've heard about stills and whatever, and petroleum refining. If you go by a refinery plant, most of those tall towers are distillation towers. In the lab, we do it here. If you have a mixture of different liquids, you can heat these up here, and the more volatile one will begin to crawl up the column here as its vapor pressure exceeds what? The applied pressure. So it depends on what pressure the system's under here. But eventually, the more volatile one comes up here. The thermometer then is a reading for the boiling point of that molecule. You can check that if the boiling point's known. And then what's this here? A water-cooled condenser, or there are different cooling means. But here the vapors can enter into that cooling chamber and begin to condense, right? Go back to the liquid state as the temperature is lowered. And then here's the receiving flask where the pure material can be collected. And then once you get all that out, you can see no more is coming up here. You can monitor that. You can take this flask off, put on another one, and then heat the pot over here at a higher temperature and bring out the next one that has the next higher boiling point. So the first one out is always the most volatile one. Okay. Any questions on distillation? So that's the physical operation in the lab to do it. This solvent chart, we saw this before when we talked about functional groups and polarity there. Here's the water solubility thing. These are all infinitely soluble. Here's some non-soluble ones. Notice acetone is infinitely soluble there. But here's what? Carbon tet. There it is. Sparingly or just a trace being in there. Ethyl ether. That's kind of an interesting one. The ethyl ether, the lone pairs, what can be hydrogen bond acceptors from water. So yeah, it's pretty soluble. We'd say that is soluble. It's over the 3 grams there. Okay. But notice THF is the cyclic ether with the alkyl groups tied back. It's still 4 nonpolar carbons. Why is THF infinitely soluble in water? Whereas ethyl ether is not infinitely soluble. It's soluble, but THF is much more soluble. Anybody see something about the structure there? It's kind of what? Yeah, it's got some symmetry to it. And what about the availability of these lone pairs in order to hydrogen bond? These are tied back, so those lone pairs are pointing out here. They're more sterically more available. So it has to do with the symmetry of the molecule and the shape of it, but that's a pretty subtle point. Okay, yeah, and hexane and the others, yeah, I think you're okay. Let's look at the vitamins. So you've heard about these in different classes maybe. You don't have to have a nutrition class or whatever to learn about vitamins. Vitamins are cofactors in biochemistry. They function with enzymes to do specific reactions, normally in metabolism. If you're lacking in your diet any of these vitamins, you've got real problems. Vitamin C is probably the most well-known one. If you don't have vitamin C in your diet, what happens to the collagen in your joints and your teeth? Uh, collagen can't form. It's required for collagen formation. Those are the fibrous proteins that hold together joints, okay, and connections between tendons and muscle, and holds your teeth in place too. You get a disease called scurvy, it's called. You don't have enough vitamin C. So we're not getting into all that, but you know something about the diseases here. Here we got the water-soluble vitamins. Now, why are these B vitamins all in the water-soluble category? A lot of functional groups there. Can you see that you have many, many what? Polar type functional groups. A lot of amines here. And that's what the vitamin Bs are. They're amine-containing ones. Niacin, nicotinamide, we'll see that in NAD, NADH, cofactor for a number of things. Thiamine and riboflavin. We got a cyclic thing here, and then a sugar. Here's a ribose sugar on there. Sugar has all these OH groups, and then pantothenic acid, carboxylic acid, and amide, and 2 alcohols. So I think you can see hydrogen bonding all over the place with water, right? Freely soluble in water at all concentrations. These tend to be cleared from the body quickly, though, out through the urine, which is, of course, an aqueous solution, right? You need to have a steady diet of these in order to stay healthy. You need milligram amounts per day, okay? Because they're cleared from the body quite quickly. So a little bit on, metabolism there. But water solubility is the key idea, I think, there. And then these are also water soluble. Another B1, B6 also has the pyridine. Oh, and a phosphate. Here I'm showing the neutral form of that phosphate. At pH 7, these 2 protons are off, and that phosphate is what? -2 charged, okay? And then, wow, cobalamin, B12, that's the most complex one. It has this corin ring here, kind of like hemoglobin, with a cobalt thing here. And yeah, a lot of heteroatoms, a lot of polar things. Folic acid, same thing there, a lot of polarity. Biotin, yeah, polar, couple of rings, and a sulfide group there. So yeah, all water soluble, I'd say. Fat soluble. These are not freely water soluble. They will tend to persist longer in the body. Why? Because urine, again, is aqueous. That's how you get rid of things, right? These are metabolized. These have to react and put more polar groups on in order for them to fall off. Where will these persist in the body? Not in the cytosol or in the blood sera. These will be found where in the body? In the interior of the lipid bilayer membrane, the nonpolar interior. And that kind of protects them. They'll hang out a long time. You need only nanogram amounts per day of these, and these will tend to persist a lot longer. So here's retinal or vitamin A. We get that from carrots, from carotene. And there it has to be metabolized in the liver. Well, wait a minute, there's an OH group there. Why is this in the fat-soluble vitamin category? There's an alcohol on that molecule. Yeah, it's exceeding that 5 carbon limit. It's got a lot more than 5. Here's the real non-polar part over here. Hydrophobic effect kicks in, right? And this will only be sparingly soluble in water. Same thing here with vitamin D. That's required for what? Bone deposition and inflammation and a number of things. Vitamin D. It's related to cholesterol. And it's a ring open form of cholesterol, actually, but just one alcohol and then a lot of non-polar things over here. Same thing for vitamin E, although we have an alcohol and an ether here. But look at this long chain here. Same thing for vitamin K, the clotting factor. If you don't have this in the blood and you get an injury, a cut or whatever, you won't clot the same way. You might have a bleeding problem there. But non-polar here, long chain here can be 5 to 10 units here, isoprene units, so very long. And then the quinone part is polar. That would tend to make it a little more water soluble, but the non-polar chain here is way more than 5. So, yeah, question.
Yeah. So take something like vitamin D.
Yeah.
You have more polar bonds and polar groups on the upper hand side. Would that be then more likely to be soluble, or could that become soluble?
Okay, so vitamin D here in this upper part, these are These are non-polar groups, right? These are just hydrocarbon groups. So that would make it very not water soluble.
What I mean is, if, I know it would change what the vitamin is, I don't even know. But if you were to add other
Oh yeah.
polar groups, then would that
Okay.
make it
So the
soluble?
question is, if you add other polar groups up here, do you increase the water solubility? Yeah, we'll see that with the hormones, testosterone and androgen and some other steroid hormones. Those have this chain off, and they have more polar groups put here. And those are hormones that circulate through the body. And so they will be more water soluble. Yeah. But right now, just looking at this one, you'd say, yeah, that's fat soluble. It's not water soluble. Okay. But no, it's a good question. And it comes up later in another topic, we could say. Okay, what about the cleaning action of soap? Molecular repentance, I like to call this. How do you get clean? Well, as materials are deposited throughout the day or weeks or years or whatever, grime and dirt build up. And, how do you get it off there? Well, if you just wash with water, yeah, the polar things will come off of a surface or your clothes or whatever. But the greasy, non-polar things will tend to stay behind. They're not soluble in water. So how do you solvate the grease stains and dirt and grime on surfaces? Well, you use a long chain fatty acid carboxylate salts. This is soap, this sodium fatty acid salt right here. And that's the carboxylic acid, what the conjugate base of it. So you deprotonate this long chain carboxylic acid. The sodium and the O minus, what? Are ionic. Those will form shells of water. This was the hydrophilic part, right? But then you have the hydrophobic chain here. How soluble is that molecule in water? Not very, okay? You have way more than 5 carbons there. And typical soaps have 16 or 18 nonpolar carbons down there. But they have the polar head group here. So that's the green ball right here. And then the orange tails here, you can see in here, are pointing in the interior. What is this? Well, this is called a micelle. This is a macromolecular self-assembled structure that is based on the hydrophobic effect. When you put this molecule in water, these chains will tend to aggregate with each other. And they'll leave the polar part, the head group, pointing toward water. And they'll tend to make these spherical shaped macromolecular structures, okay? That's called a micelle. They're critical concentrations, and they're discussions about how they form and everything, but it's based on what we just talked about there, delta S, trying to minimize that increased order of the water molecules around the nonpolar groups. So they'll bury the nonpolar things in the interior and have the polar head groups for the exterior. And so when this sees a greasy surface, it can take that grease and partition that grease or that stained material into the interior of the micelle. And then what? You can wash the micelle away, right? Okay. So soap takes time in order to clean a surface. You got a lot of nasty, dirty pans in the sink, and you think, oh, how come the soap's taking forever to clean this thing? Well, it takes a while for the grease and the stains to partition into the interior. So give it time, work out a little bit, let it soak, whatever. Okay. And it'll eventually clean there. So the micelles are water soluble, and the grease and the dirt, whatever, partitions into the interior. So that's the basis of molecular repentance there. That's how you get clean. There's a process there, okay. Questions on that? Micelles, a couple terms there. Know what those terms mean, micelle, whatever. And then we got the lipid bilayer membrane. We've been talking about this. Phosphatidylcholines, here we have a polar head group and the nonpolar chains here. And these have different topology. Instead of forming spherical balls, they'll form the lipid bilayer membrane that you know and love already from biology, right? The interior is where these nonpolar chains are pointing. Kind of looks like a frog there. And then, why is it called bilayer? Well, there's one surface here exposed to water or the exterior of the cell and one surface on the interior. There's a lot of other stuff in membranes in biology, right? There are different proteins that span the channel. There are carbohydrate tails here for the immune system, whatever. And so this is a little tiny cross-section of a living cell, right? It's this outer boundary here we call the lipid bilayer. And it's, again, hydrophobic effect, okay? These are not water soluble. They'll bury in the interior, and then you have the polar parts on the exterior that can interact with water. Okay. Question on that. So just know the basics of that. And then we have molecules that are highly Lewis basic that can donate lone pairs toward metals and actually bring metals to be more soluble in nonpolar solutions. Actually, these 18 crown 6 actually increases the solubility of ionic compounds in nonpolar solvents, kind of the reverse there. And there are many of these ionophores, they're called in biology also, that has different specificities for different metals, and that's part of their effect, how they work. They can partition metals across bilayer membranes. Because normally a metal can't get through a lipid bilayer membrane on its own. It has to be active transport. There are different proteins that can do that, or different ionophores, they're called. And once the metals get in the interior with all these lone pairs pointing at it, it becomes more soluble in that membrane area. So that's the term ionophore, which means loving ions, loving metal ions. Okay, different type of effect, but similar thing. And then looking at the molecules of life. So this is the big picture we showed you at the beginning of the course. Amino acids, the R groups here, there's 20 different ones. Those can be nonpolar in nature or polar, but the amino carboxylate, that's very polar. So those tend to be water soluble. Now when they make proteins here, there's a lot of nonpolar side chains, and those can be buried in the interior when a protein folds up. So we'll see this hydrophobic effect later on. Then we got sugars like glucose, very water soluble, right? A lot of alcohols can hydrogen bond. Lipids and fats, we just saw those, lipid bilayer membranes. There's some non-polar things going on there. And then the steroids. So the question, other hormones can have other functional groups here that change that solubility. And then DNA, you got the hydrogen bonding ideas there. So we'll have hydrogen bonding, A with T, G with C, and that's the complementary hydrogen bonding. And then why does that work? Well, you got the phosphates here, which are water soluble on the exterior of the double helix. And we'll have a lot more to say about that, obviously. And here's a drug application. We can't end the discussion without doing drugs, right? And so a number of you, I imagine, have taken some of these. Albuterol's the old one here. These are beta adrenergic receptor agonists. Don't worry about that. But I'm just comparing this more modern one, Ceravent or Flovent, with albuterol. And here's the part in black that actually binds to the beta adrenergic receptor and dilates blood vessels and bronchial tubes and lets you breathe better. Adrenergic, it's the same as adrenaline. It's the same epinephrine. Okay, it's the same effect there. Why does this one have a half-life of 12 hours? This will persist in the body. This is an all-day type drug. This one needs to be taken quite often. It's more of an emergency thing with the inhaler, right? Why was this one going to persist longer than that? Oh, well, that's the red part here. This red part is what? A big non-polar grease ball. And that's going to hold it in the membrane. In fact, the beta adrenergic receptor is membrane bound. So if the drug has a non-polar tail to it, it will tend to persist longer in the lipid bilayer membrane and be longer acting. And that's all to point out there. But do you see that? This big red part here is much bigger compared to this smaller 4-carbon tail here on albuterol. Okay. Anyway, anybody take Ceravent or albuterol? There's usually a couple people. Okay. Yeah, but people with asthma are much more familiar with those things. Okay, yeah, and like I said, we'll be starting chapter 4 on Monday. So very good, read ahead. And this is the last chapter coming up. So be working on the homework book challenge. Remember, those are the rest of the even problems at the ends of each chapter. You don't turn that booklet into me until the end of the semester, but it's a great way to prepare for the exams. Work as many of those problems as you can. Some people ask, well, can I do the odd problems also? Yes, by all means. Do as many problems as you want. Now, I've even had students go over to the library and work problems in other textbooks. We have 12 or 15 other organic textbooks over there. There's no lack of problems, right? You guys have enough problems, I think. But do as many as you can. Very good. We'll see you on Monday. Have a great weekend.